For the last two lessons of the term, we are going to transition back to number theory. So specifically, we're going to cover chapter 7 of the text. Today, we're going to see 7.1, and on Wednesday, we'll see 7.2. So specifically, we will focus on greatest common divisors, the Euclidean algorithm, and what is known as Bezout's lemma for today's lesson. And then in the next video, we will focus on Euclid's lemma and the fundamental theorem of arithmetic, which we will be able to prove using the results covered today. And we will conclude our course with applications of the fundamental theorem of arithmetic, namely proving that if we have any square-free integer n, so in other words, any number n that has no squares appearing in its prime factorization, then the square root of n must be irrational. And so we will prove that on Wednesday. But before we start chapter 7, I want us to have a quick discussion on the axiom of choice. I sent you all an email with a couple of YouTube links. One of those YouTube links discussed the Banach-Tarski paradox in further detail, specifically going into how the axiom of choice leads to this construction that if we had two solid spheres, then we can if we had one solid sphere, we can cut the solid sphere into finally many parts, actually 5. And then once we have those 5 pieces, we can rearrange them to get two solid spheres, both having the same volume. The other YouTube video went into the notion of measurability, which is covered in real analysis too. And so this extends the notion of distance in terms of measuring the distance of a set. And using the axiom of choice, one can then deduce that there are sets that cannot be measured. And so that video goes into more detail, and such a set is known as a Vitali set. Now, there's another consequence, actually an equivalent statement to the axiom of choice, which is rather mind-boggling, and it is known as the well-ordering theorem, not to be confused with the well-ordering principle that we have been using throughout the term. And so to define the well-ordering theorem, we're going to first discuss what it means to be a strict total order. And so we're going to choose A to be any set. And a relation R on A is said to be a strict total order if we have the following 3 properties. For every element of A, it is the case that A, A is not in R. So in other words, this is irreflexive. And so this is a term that is applied to any relation R that has this property, that for all A, A is not in R. Well, that's property 1 that we need. The second property that R must satisfy is that R is transitive. And finally, if A and B are distinct elements of A, so in other words, A does not equal B, then it is the case that A are B or B are A. Now you are familiar with examples of strict total orders. Less than is a strict total order on the real numbers. Because if we have for any real number A, it is the case that A is not less than itself. So we do satisfy this. Less than is transitive. And finally, if A does not equal B, then of course that tells us that A is less than B or B is less than A. And so less than is an example of a strict total order. And with this terminology, we can now state the well-ordering theorem. So for any set A, there is some relation R on A that is a strict total order. Now that comes to no surprise. What is surprising about the well-ordering theorem is the second portion, is that we have this strict total order on A that has the property that for each non-empty subset B of A, B has a least element with respect to the relation R. So you can now see how the well-ordering theorem is related to the well-ordering principle. In the case of the natural numbers, we do have that less than is a strict total order on the natural numbers, and for every non-empty set of the natural numbers, there is a least element with respect to less than. But the well-ordering theorem tells us that we can do this for any set A. We can always find a relation such that every non-empty subset of that set has a least element with respect to R. So let's think about this further. If we consider the real numbers, the Wall ordering theorem tells us that there is a strict total order, and every subset of the real numbers has a least element with respect to this relation. In other words, the real numbers have a least element with respect to this relation. Has a least element with respect to R. Now what I want to do is demonstrate how the axiom of choice allows you to construct such a relation R. And so here's the recipe for constructing R using the axiom of choice. So we have a choice of what we want the least element to be. Say that we want to have pi to be the least element. Then we can say that pi, we want to have this relation R to have pi comma a for every a in the real numbers except pi. And so this will, once we go through the construction and we make this R a strict total order, then we're going to have pi comma a. Pi is less than every real number that is not equal to a. But then you can go ahead and choose the next element, the element that is greater than pi but less than everything else. And so let's say we wanted to have negative e to be that element. So we can go ahead and choose negative e comma b to be an R. And then now we have for every b in the real numbers, but then we have to remove pi and negative e. And we can just continue in this manner and construct R in this way, working one real number at a time. But through the axiom of choice, we are choosing these elements so that we can populate this relation R to be a strict total order. And consequently, by its construction, it will always have a least element for every non-empty subset of the real numbers. Now, there is a famous saying that says, and this goes back to mathematician Jerry Bona, that says, the axiom of choice is obviously true. The Wall ordering theorem is obviously false, and who knows about Soren's lemma? Unfortunately, the last of these statements, Soren's lemma, we don't have the time to go into. But if you take courses that assume abstract algebra, then you will run into Soren's lemma. Now, where the saying is coming from with regards to the axiom of choice is that, as we saw in our last lesson, proving propositions, such as the one in front of us, where we have a function from a to b that is surjective, then we can find a function that is injective from b to a. Constructions such as that feel like they should be true. This is natural. And so this is where the obviously true is coming from. In the case of the Wall ordering theorem, Bona mentions it's obviously false because things just go counter our expectations. The notion of having a least real number goes against everything that we've been trained in mathematics, but because of the way that we construct this is perfectly fine and allowed if the axiom of choice is assumed. Due to its controversy, the Zermelo-Fraenkel axiom system for set theory is broken actually in two: the Zermelo-Fraenkel axioms for set theory and the Zermelo-Fraenkel with choice for set theory. And in the case of with choice, that is, we take the standard axioms for Zermelo-Fraenkel set theory, but then we also take the axiom of choice as one of our axioms. And so this is a statement that you'll continue to run into in your future math courses. If you take courses in real analysis, you're going to see how the axiom of choice can lead to counterintuitive constructions. In abstract algebra, it leads to intuitive constructions. And so it's something that you'll come back to in future courses. But now, let us transition to Chapter 7. And so we're going to start off with the notion of divisors, which we have used throughout the term. And so now we're going to make it precise. So let a be a positive integer. We're going to define the divisors of a as the positive integers that divide A. And so we can denote the set of divisors of A by D of A. And so that's the set of positive integers such that D divides A. Now, Bellman makes this distinction of this being true for positive integers, but we can go ahead and remove this notion of being positive and the statement still holds. So we can just say if A is a positive integer, the divisors of A are those positive integers that divide A. And so if A and B are two positive integers, then D of A intersect D of B is the set of positive integers that divide both A and B. In other words, the common divisors of A and B. And the largest such common divisor is known as the greatest common divisor of A and B, and we denote that by GCD of A and B. Now suppose that we have two integers A and B. How do we go about finding the greatest common divisor of both A and B? If the numbers are small, we can of course break it up into factors and see which is the greatest common factor they have. But for very large numbers, this is not a viable option. But thankfully we have an algorithm that dates back to Euclid that gives us a recipe for constructing the GCD of any two integers A and B, and it is based on the division theorem. So here's the Euclidean algorithm. So we choose A and B. So I took this from my number theory notes from when I taught it in the winter. And so natural numbers was assumed to not contain 0. So in this case, I'm going to go ahead and just replace this natural numbers with positive integers. And so we have positive integers A and B, and we apply the division theorem to A and B. And so by the division theorem, we get unique integers Q1 and R1 such that A is equal to B times Q1 plus R1, and R1 is greater than or equal to 0, but it's strictly less than B. If the remainder, R1, is not equal to 0, then we apply the division theorem once more. And so we attain, after applying the division theorem to both B and R1, we get B equals R1 times Q2 plus R2, and then the remainder R sub 2 now is greater than or equal to 0, but strictly less than R1. And we can continue in this step. And each step along the way, we're going to have, by its construction, that R1 is less than B, then R2 is less than B. And then if R2 is not equal to 0, we can do it again, and we get an R3. But now, each of these R sub j's is a non-negative integer. And we have a descending sequence of non-negative integers. So eventually, this has to terminate. And so there must be some R sub n that is less than all of these, that is also greater than or equal to 0. And so in the notation that I have here, I'm going to put this as a R sub n plus 1. And so this has to terminate, since we cannot have a infinite descending sequence of non-negative integers, that each being strictly less than the next. So here's an example of how the Euclidean algorithm is used. So let's say that we start off with A, 426,930, and we have B, 123,945. We apply the division theorem to both A and B, and that gives us a quotient of 3 and a remainder R sub 1 of 55,095. And so this step here corresponds to this on the right. Since 55,095 is not equal to 0, we proceed to the next step. And so now we apply the division theorem to both 123,945 and 55,095. And so that gives us 123,945 is equal to 55,095 times 2, the quotient, and now our new remainder. But that's not equal to 0, so we continue. And we do this, and we continue in this process until eventually we get to 75 equals 30 times 2 plus 15, and 15 is not equal to 0. And so we apply the division theorem once more, but then we get 30 equals 15 times 2 plus 0. And so in the notation, this 15 is the R sub n. And what the Euclidean algorithm asserts is that the R sub n, right before you get to 0, that will be the GCD. So in this case, the GCD of these two numbers is exactly 15. But I just described the algorithm. Now we're going to go through and prove that this is true. So the statement we are first going to prove is that if a and b are positive integers with a greater than or equal to b, and r is the remainder when we divide a by b, then if r is equal to 0, the GCD of a comma b is equal to b, and if r is greater than 0, then the GCD of a comma b is the same as the GCD of b comma r. So let's prove this. So let's go ahead and apply the division theorem. So by the division theorem, there are unique integers q and r such that a is equal to b times q plus r, and 0 is less than or equal to r, which is strictly less than b. So let us first consider what happens when r is equal to 0. If r is equal to 0, then a is equal to b times q. And if a is equal to b times q, this tells us then d of a, then b, let me write this way, d is in d of a, the divisors of a, and b is in the divisors of b. But b is the greatest element of d of b, and therefore it is the greatest element of the intersection of d of a, the divisors of a, and the divisors of b. So thus, b is equal to the GCD of a comma b. So next, we're going to suppose that the remainder is not equal to 0. And to make things simpler, I'm going to introduce notation. So we're going to let d be the GCD of a comma b, and we're going to let u be the GCD of b comma r. And what we want to show, of course, is that d is equal to u. So now, by definition, we have that u divides b, and u divides r, since it is the greatest common divisor of both b and r. But now, if u divides b and u divides r, we have by the linear combination lemma, which we proved in one of the lessons in chapter 3, we have that if d divides x and d divides y, then d divides mx plus ny. And so the way that this is used in this situation is that we have u divides b, u divides r. But we have that a is equal to bq plus r. And so consequently, u divides a by the linear combination lemma. So here, mx plus ny, we are treating it as bq plus r. So by the linear combination lemma, we have that u divides a. But now, so just in particular, u divides both b and u divides a, which implies that u is in the intersection of the divisors of a and the divisors of B. But if U is in here, it has to be, by definition, less than or equal to the GCD of A and B. So consequently, U has to be less than or equal to D. And so we got this inequality. So now what we are going to show is that D is less than or equal to U. So next, so we're going to observe that the remainder R is equal to A minus B times Q. Because the way we took our, by applying the division theorem, we have A is equal to BQ plus R. Now, since D, which is the GCD of A and B, since D divides A and D divides B, we have, by the linear combination lemma, that D divides R. And so here we use the linear combination lemma once again. But now if D divides R and D divides B, we get that D is in the intersection of the divisors of B with the divisors of R. But U is equal to the GCD of B and R. So it is the greatest element of this intersection. And thus, we get that D must be less than or equal to U. And since U is less than or equal to D, and D is less than or equal to U, we deduce that they must be equal. So this statement right here is actually one of the axioms for the integers. And so this is known as the trichotomy axiom. And so U less than or equal to D, D is less than or equal to U. If we have both of these inequalities being satisfied, U must be exactly D. But that's what we wanted to prove, that we had the GCD of A comma B equals the GCD of B comma R, and so that finishes the proof. And so we're done with theorem 712. And now we can prove that the Euclidean algorithm does in fact give us back the GCD. So take A and B to be positive integers, and we're going to perform the Euclidean algorithm to A and B, and we're going to let R sub n be the last non-zero remainder outputted by the algorithm. And then the claim is that the GCD of A comma B is equal to Rn. And the proof is just a consequence now of theorem 712. So now, so by the Euclidean algorithm, we have n equations, and so we have here A, B, Q1 plus R1, then we have B equals R1, and then a second quotient plus R2, and this continues until eventually we get to R sub n minus 2, which is equal to R sub n minus 1, the nth quotient plus the nth remainder. And so we have these series of equations. But by theorem 712, we have that the GCD of A and B is the same as B with its remainder, which is now R1. But then we apply theorem 712 again, and it tells us that if we took B and R1, that will R1 and R2, that GCD will be the same. And so we have R1 comma R2. And then we just get a string of equalities until eventually we get down to R sub n minus 1 comma R sub n. But now R sub n, by assumption, is the last non-zero remainder. And so what that's telling us is that if we were to have done the Euclidean algorithm one last step, we will have an R sub n minus 1 is equal to then R sub n and then Q sub n plus 1 plus 0. And since we have remainder 0 here, we come back to theorem 712. And theorem 712 tells us that if the remainder, when we divide a number by b, is 0, then the GCD is going to be b. And so in this situation, we're going to have that the GCD of Rn minus 1 comma Rn, since the remainder is 0, it will be R sub n. And that's what we wanted to prove. And so now we are done with the proof that tells us that the Euclidean algorithm does in fact output the GCD of A and B. Now for homework, you'll have a couple of questions that will have you use the Euclidean algorithm. So you'll be given two elements, A and B, asked to compute the GCD, and the main thing is apply the division theorem several times until you get to the situation where you know that the remainder is 0. And then the previous non-zero remainder, that's the GCD. So next, we are going to prove an important result known as Bezout's lemma. It is with Bezout's lemma that we will be able to prove the fundamental theorem of arithmetic in our next lesson. So what does Bezout's lemma tell us? Well, we have integers a and b such that a equals b is not equal to 0. So in other words, a and b are integers such that both a and b are not both equal to 0. And we're going to let d be the GCD of a and b. Then Bezout's lemma asserts the existence of integers x and y such that ax plus by is equal to d. In our textbook, this is theorem 714. And in the book, it's done under a weaker assumption, namely that a and b are both positive integers. So I'm going to remove the restriction to only the positive integers and allow all integers so long as both a and b are not equal to 0. Some history before we continue. The statement is not actually due to Bezout, but to Claude Mesuriac, who proved it in 1624. Now, Bezout proved this statement in 1799. He generalized in his proof Mesuriac's original statement to polynomials. And then over a century later, Emmy Noether realized that there was nothing special about the integers or polynomials, but that this held for a wider collection of objects, which she coined principal ideal domains, and these are studied in abstract algebra. In fact, the paper where she demonstrated this is one of the foundational papers for the theory of abstract algebra. And so if you take a course in abstract algebra, you will see this statement in its more general setting. So let's go ahead and prove Bezout's lemma. And so for the proof, we're going to let d throughout the proof be the GCD of a comma b. And we're going to construct a set. And so first off, since we know that both a and b are not both equal to 0, so by assumption, we know that a is not equal to 0 or b is not equal to 0. And so with all loss of generality, we may assume that a is non-zero. Now what we are going to do is construct a set. And so let S of a comma b be the collection of positive integers u such that there exist integers x and y such that ax plus by is equal to u. And since this here is a subset of the positive integers by construction, and so this is a subset of the positive integers, and now we want to use the well ordering principle. But to use the well ordering principle, we need to show that this is non-empty. So let's show that. So note that if we do A times 1 plus B times 0, this is equal to A, and A times negative 1 plus B times 0 is equal to negative A. So consequently, 1 of A or negative A is a positive integer, and thus S of A comma B is non-empty, because we have that if A were the positive integer, then A must be in that set. If negative A is the positive integer, then it must be in this set, since to be in S of A comma B, we need to have two integers x and y, such that ax plus by is equal to the given u. And so here we chose 1, 0, negative 1, 0 for x and y respectively. So we have S of A comma B is non-empty. Well ordering principle comes in, tells us there is a least element. Let's call it L. And so by the well ordering principle, S of A comma B has a least element, and let's go ahead and call that element L. And so we claim that L is equal to D, because that's what we want to prove. We want to show that we have x and y, but the beauty of this set S of A comma B is that it already has the given x comma y. And so now we want to show that the least element is in fact the greatest common divisor of both A and B. Since L is an S of A comma B, there are integers x and y such that L is equal to ax plus by. But now we know that D divides A, D divides B, and so by the linear combination lemma, D divides L. And since D divides A, or let me write this way, since D is the GCD of A and B, we have by the linear combination lemma that D divides L, and thus D is less than or equal to L. Since we also have this statement here that if D divides a number, then D has to be at most that number if we're dealing with positive integers. Okay, so we have D is less than or equal to L. Now we're going to apply the division theorem. So by the division theorem, there are unique integers Q and R such that, and so we're going to do the division theorem, but we're applying it to both A and L. And so we're going to have that A is equal to L times Q plus R, and now R satisfies the inequality 0 less than or equal to R, which is less than L. Now if we solve for R, so now observe, so we solve for R, we get R is equal to A minus L times Q. But we know what L is in terms of that L is equal to ax plus by. So we get that A minus L, and now we replace L with ax plus by times Q. And so now this gives us a minus axq minus byq. Let's go ahead, rearrange things. So now if we factor an a out, we have a, and then we have a 1 minus xq, and then we have a minus byq. And as of now, this seems rather innocent, except for one thing. We have, in this situation, I'm going to rewrite this over here, the minus byq, I'm going to write this as plus b, and now negative y times q. And what does this remind us of? This is what it means to be in the set S of a comma b that we have. Our set is defined to be the numbers, all the numbers of the form ax plus by that are positive integers, where x and y are now arbitrary integers. But now we have something of the form a times a new x plus b times a new y equals r. And so we got this here. So here's what happens now. So if r were positive, then r must be an S of a comma b. But this is a contradiction. Since r is less than L, and that's where we use the division theorem. We have that r is less than L, and L is the least element. Of S of a comma b. And so that's a problem. So it must be the case that r is equal to 0. So we conclude that r must be equal to 0, since r has to be between 0 and L, but it can't be positive, so it must be exactly equal to 0. And thus, we get that a is equal to L times Q. But if a is equal to L times Q, that means that L divides a. So we got L divides a. But notice, this argument was attained by doing the division theorem to a and L. What if we do it to b and L? And so what I'm going to do now is come back to this portion of the argument and do the division theorem for b and L, and then that will result in q prime and r prime. And so over here, this is going to become a b, and this here will be q prime, r prime, and we have r prime is less than L. And the only difference is that when we go through the argument here, now when we solve for r prime is going to now be b minus L times q prime. And so we have b, but we still have ax plus by for L. And so here we have a q prime. And so now this here becomes a b. And let me just go ahead and just do this portion again. So now we have b minus ax q prime minus by q prime. We go ahead, factor out a b, and that gives us a 1 minus yq prime, and plus an a, and then a negative xq prime. And then we have, the argument continues, if r prime is greater than 0, then r prime is in S sub a comma b, but now this is a contradiction, since L again is the least element of S sub a comma b. And so it must be the case that r prime is equal to 0, and so that tells us that b is equal to L times q prime, and therefore L divides b. So we got L divides A and L divides B. So consequently, L is in the set of divisors of A and B. Since D is the greatest element in that intersection, we get that D is less than or equal to L. But we have just shown, just a moment ago, that D is less than or equal to L. Oops, and I made the inequality here incorrectly. L has to be less than or equal to D, since D is the greatest element in the set of in the intersection. And so L is less than or equal to D, but we already know that D is less than or equal to L. And thus, or I should say hence, L is equal to D, and we're done. Because if L is equal to D, that means that the GCD is equal to AX plus BY. And that finishes the proof of Bezout's lemma. And in our next lesson, we will now be able to prove the fundamental theorem of arithmetic thanks to this result. As a consequence of Bezout's lemma, we get that if A and B are relatively prime integers, then we can find integers x and y such that ax plus by is equal to 1. Because if you are relatively prime, then the GCD is 1. And so Bezout's lemma tells us that we can always find integers x and y whenever a and b are relatively prime, so that ax plus by equals 1. To finish it off for today, we're going to prove theorem 716. And so I'm going to go ahead and do that. We don't need to have the positive integers portion in here, so we can just do this for integers. And so for the proof, so we have d divides a and d divides b. And so suppose d divides a and d divides b. Then there are, let's go ahead and call them k and l. So integers k and l, such that a is equal to d times k and b is equal to d times l. Next thing is apply Bezout's lemma. By Bezout's lemma, there are integers x and y such that ax plus by, which is in this notation equal to d and then kx, and then b, which is d times l, we factored out the d, so this is going to be l times y, and this is equal to the GCD of a comma b. Hence, d divides the GCD of a and b. And so now we have that anytime that we have a common divisor of a and b, it must automatically divide the greatest common divisor. And so that finishes for this proof, and we are done for today's lesson. In our next lesson, we're going to start off by proving what is known as Euclid's lemma, and we're going to be using Bezout's lemma to prove it. And so Euclid's lemma tells us that if we have a prime p, and we have two integers a and b, such that p divides a times b, then p divides a, or p divides b. And that's the missing link for proving the fundamental theorem of arithmetic. And so that will be for our next lesson.